So I mentioned that part of this chapter deals with being able to expand any binomial raised to any power. You can take something like 3x minus 5y to the power 10, and instead of multiplying that binomial out 10 times, doing all that simplifying, we can use this binomial theorem to actually do the expansion in a fairly quick and methodical way. Doesn't matter what the binomial is. So as a warm-up, we'll start to look at some expansions and recognize some patterns. So what we have here is we have the expansion of x plus y to the power n, starting with n equals 0 all the way up to n equals 6. So those expansions are there for you. And again, we'll start to see some patterns forming here. First pattern is this, right? That last term, if we just look at the last row, I should say, where n is 6, if you count up all the terms in that expansion on that bottom row, there are actually 7 terms there. If you look at the second row from the bottom, where n is 5, and you count up all the terms, there's actually 6 terms there. And that pattern will continue. The number of terms is always one more than the value of n. N refers to the power on the binomial. So we say that there are n plus 1 terms in each expansion. The next line talks about the sum of the exponents of x and y in each term. Let's look at that last row. You've only got one exponent in the first term, 6. Second term, it's x to the 5th, y to the 1. When you add the exponents together, you get 6. Same thing with the third term. Exponents are 4 and 2. Add them together, you get 6. That happens every term. Not only in this bottom row, but if you skip up to the row above, where n is 5, the sum of the exponents in each term is 5. So, the sum of the exponents of x and y each term is equal to n, whatever the power on the binomial is. The next line talks about what's happening to the exponents of x. Now in this term here, or case here, we're doing the expansion of x plus y to the n. Okay? X is the first term of the binomial, y is the second term. When we talk about what's happening to the exponents on x, in this case, they are x and y variables, but they can be any variable we want. But the pattern will be the same. And if you look at what's happening to the powers on x, in each case, it starts at n and it decreases by 1. For this last row, where n is 6, the first term of the binomial is x, and that first term is x to the 6th. The next term is x to the 5th, then x to the 4th, then x cubed, and so on. Same thing happens in the row above, where n is 5. The first term is x to the 5, and that power again decreases by 1 as you go term to term. And it also works for the last term, because the last term would be x to the 0. So in every case, the exponents of x decrease term by term, starting with n and ending with 0. Okay, Serena? What about the exponents of y, which is the second term of the binomial? Well, if we look at this last row, it's just x to the 6th, but that's the same thing as x to the 6th, y to the 0. The next term is y to the 1, then y squared, cubed, 4th, 5th, all the way up to 6. Same thing with the row above. The second term is y. The first term of the expansion is y to the 0, then y to the 1, 2, 3, 4, ending in y to the 5. So in every case, the exponents of y increase term by term from 0 up to n. The last row or number says coefficients in each expansion form a what kind of relationship? Well, if we look at the coefficients, it's 1, then 1, 1, then 1, 2, 1, then 1, 3, 3, 1, and so on. So if we write them out here, and we can keep going. And I don't have room to write that next row, but that's fine. What we see happening here is that these coefficients from all those terms, they form a symmetrical arrangement. That's what's happening. Each row starts with a 1, ends with a 1, and there's some symmetry there. Especially when you look at this row, all the terms are symmetrical about the middle. In the previous row, the terms are symmetrical about the middle number. So really, in each case, those numbers are symmetrical about the middle. Sometimes the middle's a blank, sometimes the middle's a number. But in each case, each row, the coefficients form a symmetrical arrangement. And those coefficients in the above expansion can be put in a triangular array, which we did up top already. This is known as Pascal's triangle. It was named after Blaise Pascal, who developed applications of the triangle in the 17th century. And speaking of someone that was born in the 17th century,
who would have known that was coming? Yeah.
I don't know how. What can we do for you today?
Mr. Widener, I need to see him again. Not now.
Okay.
Stay for your lesson.
He'll come down.
Okay.
Yep. Okay, so this is Pascal's triangle, and this can be used to find those coefficients. And there is a pattern here, right? It's not just getting them from the coefficients after the expansion. You can get the coefficients first. There's a pattern here. Each row starts with a 1 and ends with a 1. That's true of the first row. That's true of the second. It's true of all of them, right? But after we get past the second row, to generate this 2, you simply add the two numbers directly above. 1 plus 1 gives you that 2. Each row starts with a 1 and ends with a 1. This 3 comes from adding the two numbers directly above. 1 plus 2 gives you that 3. 2 plus 1 gives you that 3. The next row starts with a 1, ends with a 1. This 4 comes from adding the two numbers directly above. 1 plus 3 is 4. 3 plus 3 gives you the 6. 3 plus 1 gives you the 4. That pattern continues forever. So this Pascal's triangle is one way that we can start to generate the coefficients for an expansion. That's only part of it, though. The other part of it is knowing how many terms you have and what's happening to each power. And again, we go back to what we've seen above here. There's always one more term than the power, the value of n. The sum of the exponents in each term always is n. The first term of the binomial, you start with that term, and the first term of the expansion is x to the power n, and then those powers decrease as you go term to term. The second term of the binomial, in this case y, starts at power 0 for the first term of the expansion, and those powers increase as you go term to term. So putting all this together, you can expand any binomial raised to any power very easy. Now on the next page, it shows that you can use Pascal's triangle, but you can also use combinations to generate those coefficients. The top row of Pascal's triangle is 1, and that can be found by going 0C0. Do 0C0 on your calculator, you'll get 1. The next row are a set of 1s, which you can get by going 1C0 and 1C1. So notice that, again, these are in the form NCR. N starts at 0 and increases by 1. And R also starts at 0 and increases by 1 as you're going across the rows. Okay? So you can also get those numbers using combinations, and we're going to see fairly quickly here that there are some times where we're going to use combinations. It's just easier. So again, Pascal's triangle is simply made up of combinations. So in this lesson, we might be asked to expand a binomial or simply find a term in the expansion. The above warm-up leads to the general formula for binomial expansion known as the binomial theorem. If you have x plus y to the power n, that is nc0 x to the n, then nc1 x to the n minus 1, and then now in the second term, you're going to get y to the 1, and then nc2 x to the n minus 2, then it's y squared, and so on. But the general term of the expansion, x plus y to the power n, is this formula right here. That's on the formula sheet. It is the k plus first term in the expansion, not term k. So notice that this general equation involves n, which is the number that you're choosing from, and then k. And this equation is used for the k plus first term of the expansion. So we're going to see how you determine what k is. N is the power on the binomial. And we're going to see that k is always one less than the term number, because you see, if you want to find the third term of an expansion, k has to equal 2, because we have the t sub k plus first term. If you want to find the third term, k plus 1 would have to equal 3, so k would have to equal 2. The value of k is always 1 less than the term number. Because sometimes you might be asked just to find a specific term. Now, you could do the entire expansion and then go back and see what, in this case, the third term is, right? Or you can just use the formula. Let's do this one both ways. Let's start and do the entire expansion of x plus y to the power 7. So there's a couple different ways we can generate these coefficients. One of them is using Pascal's triangle. Remember, each row starts with a 1 and ends with a 1. In each case, you add the numbers together that are above to get each number. Because in this case, n is 7, it's x plus y to the power 7, that means you have to have 8 terms. The number of terms is always 1 more than n. So right now, we only have 6 coefficients. We need to generate 2 more rows to get 8 coefficients, because we need 8 terms. So this is the row that we're going to use for our coefficients. And note that again, each row starts with a 1, ends with a 1, but the second number, in this case is 7, matches n. Okay, Miriam? So don't lie to me, because deep down you're not sorry. So there's another way you know which row you need to stop at. One way is that there's always one more term than n. So we need 8 terms, so we have to have 8 numbers, which we now have. The other way, the second number matches the value of n. So we'll start with our coefficients. 1, 7, 21, 35, 35, 21, 7, 1. The first term of the binomial is x, and that starts with a power that matches n, x to the 7. And then the powers decrease by 1. And you can write that last term being x to the power 0 if you want. Not necessary. The second term of the binomial is y. The first term of the expansion starts at y to the power 0, and then it increases by 1. And we can start putting pluses in between these terms. Could have done that any time. If you look at each individual term, if you add the exponents together, in each case, you get 7, which matches or equals n. So you might just simplify really quick. X to the 7th plus 7x to the 6th y, and so on. So there's the entire expansion. And we were asked for the third term, which would be 21 x to the 5th y squared. That's one way to get it. And you know, technically, you didn't have to keep going after the third. You could have stopped there. You would have had it. So that's one way. The other way is using this general term formula. So using t sub k plus first term is nck x to the n minus k y to the k. We want the third term, so again, k has to equal 2. To get t sub 3, which represents the third term, using this general term expression, k has to equal 2. Again, k is always 1 less than the term number. So that will equal 7c2. Remember, n is the power on the binomial, which is 7. The first term of the binomial is x to the power 7 minus 2 times y to the power k, which again is 2. If we go to our calculator, 7c2, try that again. 7c2 is 21. X to the 5th, y squared. Same answer. Same answer. And again, I got these coefficients here when I did the expansion by using Pascal's triangle. I also could have used combinations. This first term, because n is 7, would be 7c0, and then 7c1, 7c2. This one here, this 35, would be 7c3. So just to check and confirm that, 7c3 does equal 35. So you can also use combinations instead of Pascal's triangle to get those coefficients. Number 2, determine the middle term in that expansion. We're going to do this using the general formula. How many terms will there be in this entire expansion, Serena? You don't know what your middle name is? Because that's what I just asked. Yeah, that's your middle name?
Yeah.
What's your first name? Hard to pronounce? Okay, fair enough. That really wasn't the question I asked.
Yeah, no.
The real question I asked is how many terms would be in this expansion? You better pop on that. Oh, come on, it'll be fun.
No, I'm good.
Is she right, Miriam? How many? The one number of terms is always one more than n. So there's 9 terms. So which term will be the middle term, Miriam? You sound so confident. Yes, the 5th one would be the middle term. So we want to find the 5th term. And using the general term formula, k would then be 4. Remember, k is always 1 less than the term number. To get the 5th term, k has to be 4. So n is 8. It'll be 8c4. In this case, the first term of the binomial isn't just x. It's 2x to the power n minus k times the second term of the binomial, which is not y. In this case, it's negative 3 to the power k. I'm just using that general term formula. It's one that's on the formula sheet. T sub k plus 1 equals nck x, which refers to the first term of the binomial, to the power n minus k times y to the power k. So 8c4 is 70 times 2x all to the power 4 would be 16x to the fourth, and negative 3 all to the power 4 would be positive 81. So we need to multiply those three coefficients together. 70 times 16 times 81. There's our final coefficient, 90,702 x to the fourth. There's that term. And this is the type that you're more likely to see on a diploma exam. It's not just as simply as x plus y raised to some power that you're working with. Number 3 kicks it up a little bit because both terms involve x, but that first term, instead of writing it as 1 over x, we'd look at it as x to the negative 1 plus x squared all to the 6. We want to find the fourth term in the expansion. So again, k is always 1 less than the term number. K would be what, Moyen? Can you help her, Earl? You got to pop on that. K is always 1 less than the term number. We want to find the fourth term. So k equals 3. Term sub 3 plus 1 will give us the fourth term. So that equals, again, NCK, 6C3. The first term in this binomial is x to the negative 1 to the power n minus k times the second term, which is x squared to the power k. 6C3. C3 is 20. And then you're going to have x to the negative 1 all cubed, x to the negative 3 times x to squared all cubed, which is x to the 6. So in this case, you can combine those two factors of x by adding the exponents, and your final answer is 20x cubed. So number 4, we want to expand that. There should be 4 terms. Instead of using Pascal's triangle, let's use combinations. The first coefficient would be 3c0. We start with 3 because that's n. And then as we go along here, all that's going to change is our r values will increase by 1. So the first term coefficient initially will be 3c0. The next term will be 3c1, 3c2, and then 3c3. The first term of the binomial is 3x. The first term in our expansion starts with that to the power n, the power 3. And then that power decreases term by term. The last term of the binomial is negative 4. The first term in the expansion starts with that last term of negative 4 to the power 0, and then those powers increase by 1. Finishing up with that last term to the power n. So now we can work each of these ones out. 3c0 should be 1. Yep. And 3x all cubed is 27x cubed times negative 4 to the 0, which is 1, plus 3c1 is 3, times 3 squared is 9 times negative 4 to the 1, or negative 4, gives us negative 108 as our next coefficient. And that'll be x squared. The next term is going to be positive because the negative 4 is all squared. But first it starts with 3c2, which is also 3. Times 3 times negative 4 all squared is 16. Gives us 144. And the last term will be negative because the negative 4 is cubed. 3c3 is 1. Times 3x all to the power 0 is also 1. So right now we have 1 times negative 4 all cubed, which is negative 64. So the final answer will be 27x cubed minus 108x squared plus 144x minus 64. So there's the final simplified, or the final expansion. So this next one shows a slightly different way you can be asked to solve a problem involving binomial expansion. One term of the expansion x plus a to the power 10 is 3,281,250x to the fourth. Determine the numerical value of a. Remember, the word determine means show your work. We know what n is in the expansion of x plus a to the power 10. N is 10. The first term of the binomial is x. The second term will be represented by a. We need to figure out what k is. What is the value of k? So let's start building the general form equation. It'll be 10ck. It'll be x to the 10 minus k times a to the power k. And we're looking for when that equals 3,281,250 x to the fourth. So Miriam, what does k equal? Better pop on that. I don't know. I'll play your silly game. Is it 11? You think so? Jonathan,
Six.
why 6?
Because x10 minus 6 equals x.
The power on x must equal 4 at the end. So 10 minus k, which is the power on x in our expression, has to equal 4. So therefore k must equal 6. And this just proves it. Boys rule and girls drool. Proves it. I don't know. I'd ask for a show of hands if people thought I was going too far, but I think you wouldn't be happy with the outcome. So we'll just leave it. We'll move on. So k has to equal 6. And that's all we needed. To be able to solve for a. So 10c6. 10c6 is 210. You have 210 x to the power 4. I should have put the 6 in there. A to the 6th equals 3,281,250 x to the 4th. So we can divide both sides by x to the 4th, and they cancel. And we can also divide both sides by 210. And this will give us what a to the 6th equals. 3,281,250 divided by 210, 15,625. A to the sixth has to equal 15,625. Then to find out what A is, we'll take the sixth root of both sides. The sixth root. Why I keep wanting to write 3. Sixth root of both sides. And that'll give us A equaling 6. Math number 5 in the list is the x root of the previous answer. A equals 5. Number 6, if one term in the expansion 3x plus by to the fourth, where b is positive, greater than 0, is 216 x squared y squared, find the value of b. So this one will be done exactly the same way. N is 4 because that's the exponent on the binomial. Our general term formula is nck. We'll have 3x to the n minus k times by to the power k. And in this case, it must equal 216 x squared y squared. So Sant, what must k equal? Can you help him, Juris? Why 2? The exponent on x has to be 2. So yes, 4 minus 2 has to equal 2. The other way is the exponent on y has to be 2. That's another reason why k must be 2, because when you look at this last factor, by to the power k, again, the exponent on y must be 2. If you let k equal 2 on x, you're going to get 4 minus 2, which will give you an x squared. It'll also give you a y squared. So yes, k must equal 2. So 4C2 is 6 times 3x all squared would be 9x squared times b squared y squared must equal our 216 x squared y squared. We can divide both sides by x squared and y squared. And they'll cancel. So what we have left is we have 6 times 9, which is 54, times b squared equals 216. Divide both sides by 54. B squared will equal 4. And normally when we're solving, taking the square root of both sides, we'll get 2 answers, a positive and a negative, but we're told that b has to be greater than 0, so only positive 2 works. Only positive 2 works. So we'll spend one more day talking about this, Pascal's triangle, binomial expansion. We'll also see some questions how it can relate to our pathways. Remember we did pathways, how many different ways you could go from point A to point B if you're following basically a grid. We saw that you can do that using combinations. But we'll also see that we can do it using Pascal's triangle. So those are the questions you should be working on for practice. I'll post the solutions to Google Classroom. On Wednesday will be our last lesson, not only of this chapter, but of Math 30-1. So the following class, which will be the following Monday, right? Because Friday is a PD day. You are right. So Tuesday will be a quiz on chapter 11. I will give you next class the review assignment for chapters 9, 10, and 11, so you can start working on that as well. Because next week will be your last exam, and then we'll start reviewing for diploma, and you'll also get the opportunity to do your rewrites if you want. Right? Yes. Okay, and remember, Friday, June 9th, last day to hand in any missed assignments. So don't leave that too long. After that, they go in as